Now that we know what the gradient vector is, we're going to practice using it in different ways. But first, let's just practice doing some calculations. So given a function, find the gradient vector. So for this first function, I see two independent variables, so I automatically know my gradient vector will have two components. One component will be the partial of my function with respect to x. Second component will be the partial of my function with respect to y. So a partial derivative for each independent variable. The x partial would become 2x minus y. The y partial would become minus x plus 6y. That's our gradient vector. For the second function, I again see two independent variables, so I know I'll have two components to my vector. The first one is the partial of my function with respect to x. So noticing that x only shows up once right here, I can treat cosine of 3y as a constant coefficient. Then multiply by the derivative of sine 3x, which would come out to be 3 cosine 3x. And then we'll do the same thing, but for the partial with respect to y, noticing y only shows up once, so the sine 3x looks like a constant multiplier, and I'm going to multiply that to the derivative of cosine 3y, which would be negative 3 sine 3y. And this doesn't really clean up that much. The only thing that we could really do is move this negative to the front of the second component, but other than that, this is a perfectly fine answer. This last one, though, you have a couple of options on how to calculate each of your partial derivatives. If you'd like, you could use the product rule, or if you prefer, you can multiply it out. Choose your own adventure. Do it however you feel most comfortable with. I'm going to use the product rule. So with the partial derivative with respect to x for this whole function, I'll take the derivative of my first function with respect to x, so I get 2x times the second guy, plus my first function times the derivative of the second guy. So that's my partial with respect to x. I'll use the product rule again for the partial with respect to y. So I get negative 6y times 2x plus y, and then plus x squared minus 3y squared times the derivative of 2x plus y with respect to y is just a 1. If you didn't use the product rule and instead multiplied out your binomial first, your answer might look different than this, but if we distributed everything and cleaned it up, they would be identical, assuming I didn't make any mistakes. Let's talk about some of the properties of this gradient vector and the directional derivative. So we now know that we can calculate a directional derivative for a function f simply using the gradient of f dotted with the unit vector that we are talking about. And if we think back to when we first learned about dot products, we learned that if we dotted a vector u with a vector v, that it was really the same thing as multiplying the magnitudes of each vector times the cosine of the angle between them. So if we're looking at the dot product of the gradient of f with a unit vector u, when we take the magnitude of each one of those things and then multiply by cosine, we're just applying that other dot product rule. But if u is a unit vector, the magnitude of this is 1. So really, the dot product of gradient f with unit vector u, it's just the magnitude of our gradient vector times cosine theta. And that's what we have over here at the top of the screen. So if we want to calculate a directional derivative for a function f in the direction of a unit vector u, we only need to find the gradient vector, its magnitude, and then multiply by cosine of the angle between the gradient vector and the unit vector u. Now sometimes finding that angle is more work than it's worth, so make sure that you're choosing the easier route. If you have the components of both vectors, grad f and unit vector u, then just multiply corresponding components, add them up. But if for some reason you know the angle between gradient f and the unit vector u, then maybe this is a shortcut for you. Anyways, that was just to remind you that we do have another definition for the dot product. And now that we remember that, hopefully, we can talk about how that influences the maximum and minimum directional derivatives. So looking at the directional derivative in the definition magnitude of gradient f times cosine theta, if we wanted to talk about maximizing that, then we want to find the max value of the gradient f magnitude times cosine theta. Now f is a surface. It's a surface that we're not changing. We're not picking, we're not going to change anything about that surface. We're simply just asking how that surface changes. So this gradient f, it's not something that you have any control over. That is completely determined by the surface f. The magnitude of that would also then be predetermined by the surface f. So this you can think of as like a fixed number. So it's just some number, and we're multiplying it by cosine theta. And remember that theta is the angle between the gradient vector and the unit vector that we are taking the directional derivative in. So if theta is the angle between these two things, we can change that angle. In other words, we can change the direction for u hat so that cosine of that angle is the largest value that it can possibly be. And maybe we remember that cosine theta is between 1 and -1. So the largest value that cosine theta could take on is 1. Which means theta would have to be equal to 0. So cosine at 0 is equal to 1. So how do we maximize our directional derivative? We need to pick a unit vector, u hat, that creates an angle of 0 with the gradient vector. If we have an angle of 0 between the gradient vector and u hat, that's the same thing as the two vectors being parallel. So how do we maximize the directional derivative? We travel in the direction of the gradient. When we travel in the direction of the gradient vector, we do create the maximum directional derivative. Which we can calculate by replacing cosine theta with cosine 0. Cosine 0 is equal to 1, so the maximum directional derivative is simply the magnitude of the gradient vector. And this is one of the reasons why the gradient vector is so powerful. Not only was it a shortcut so that we could bypass the limit definition of a directional derivative, but also it's telling us how to maximize that directional derivative and how to compute what the maximum directional derivative is. So let's use the same thinking to find the minimal directional derivative. So if traveling parallel to the gradient vector gave us an angle of 0, which maximized our cosine theta, let's think about what the minimum value of cosine theta is. Cosine theta can be equal to 0, but the real minimum value is -1. The theta that we would need to get cosine theta equal to -1 is pi. So this would be like traveling opposite of the gradient vector. If I want to pick u so that theta is equal to pi, then I am traveling opposite of the gradient vector. And if we travel in the opposite direction of the gradient vector, so if we pick u hat so that theta is equal to pi, then the minimum directional derivative occurs, and it looks like the magnitude of the gradient of f times cosine at pi. Cosine at pi is equal to -1. So really, the minimum directional derivative is simply the negative of the magnitude of the gradient vector. One last property about the directional derivative, and that's us talking about when is the directional derivative equal to 0? Well, if we think about the definition that we have been working with on this slide, the directional derivative is the gradient of f, magnitude, times cosine theta. Now remember that the magnitude of the gradient f, we don't have any control on that. That's essentially a fixed number. It's the cosine theta that we're allowed to change, and that changes based on which u hat we pick. And we can make cosine theta equal to 0 if we pick u hat so that it's perpendicular to the gradient vector, because cosine at pi over 2 is equal to 0, and 0 times a number is equal to 0. So the directional derivative is equal to 0 in the direction u hat, where u hat is perpendicular to our gradient vector. So maximizing a directional derivative, minimizing a directional derivative, or nulling, making it 0, all depend on the gradient vector, either traveling parallel to it, opposite to it, or perpendicular to it. With this idea in mind, let's practice finding a maximum directional derivative. So we're asked to find the direction for which the directional derivative of the function f at the point -2, 3 is a maximum. First thing I want to highlight to you is what the question is asking of you. First, it says find the direction. If we're asking for a direction, then we need to give an answer like u hat. So for this first direction, or first question, the answer is going to be a vector, u hat, that tells you which direction you should travel in to reach the maximum directional derivative. It's not asking for the maximum. It's not asking you to calculate the maximum. It's asking you to find the direction for that. So let's go ahead and do it. On the last slide, we said if you want to maximize your directional derivative, you need to travel parallel to the gradient vector. We can't be parallel to something if we don't know what it is, so let's start off by calculating gradient f for our function. We have our gradient vector f. We need to find that gradient vector at the point -2, 3. Simplify that down. I get the vector -24, 20. Although technically this is the direction we're traveling in, when we're asking for a direction, we like conventionally to use unit vectors. So not only is this the gradient vector, but now we're going to find the unit vector u hat that's parallel to the gradient vector at that point. And to find that, we're going to find the magnitude of the gradient vector so that we can divide it off. So let's do some scratch work over here. Magnitude of our gradient vector looks like negative 24 squared plus 20 squared square rooted. Typing that into the calculator, I'm finding that simplifies to be the square root of 976, and that simplifies even further to be 4 square root 61. So the final answer for that first question is u hat should be equal to negative 24 over 4 root 61 in the x direction, and then positive 20 over 4 root 61 in the y direction. This does simplify, so it would be a shame if we didn't simplify it. Let's go ahead and do that. We get negative 6 over root 61 for the x component, and then 5 over root 61 for the y component. Now, I'm not going to rationalize this because it's just numbers, it's not a function, and in my opinion, there's no need to rationalize this, so I'm not going to, but if you want to, feel free. But remember, that is only the answer to the first question. There was a second question. Second question was, what is the minimum value? To find the minimum value, we needed to travel in the opposite direction of the gradient vector. So this would be like using opposite of u hat. When we traveled opposite of the gradient vector, we found that the directional derivative just looked like negative magnitude of gradient f. We know what gradient f is. It's 4 times the square root of 61. So the minimum value of the directional derivative would be negative 4 square root 61.